Hello, my name is Donovan Gray, and this is my lab report of lab number 1 charge tapes. We're in physics 2, and I'm going to go into the introduction real quick. Basically, this whole entire lab is about the charging of insulators, specifically the charging of Scotch tape and the interactions between two pieces of charged Scotch tape, and we're trying to demonstrate the magnitude of the charge gathered on the piece of tape as we give it a charge. As we know from scientific or as we know from the scientific properties of insulators, whenever you have two insulators together and they get rubbed together, they generate a charge. And when they generate a charge, we can test to see the magnitude of that charge by holding them close together, and we can see the displacement that they make. And if we compare that to another force acting on it, like gravity, once it gets in equilibrium, we know that the two forces are matched, and we can then measure the force of gravity, and then that will, in fact, tell us the force of the electric field, or the electric force caused by the electric field of another tape on that top piece of tape. We found that the tapes had a positive charge of 4.9 nanocoulombs when we ripped it off of the table. That's just a little introduction into the results that we got from the lab. On the next slide, I'm going to talk about the model. So this model shows a little bit more about what it looks like, or how we can model it when we're calculating the two charges. Of course, they are not point charges. They are actual pieces of tape. However, we can model them as point charges for reasons I will get into later in the presentation. However, the top blue point charge is representing the upper piece of tape, and it has a lower force of gravity pointing down and an upper force from the electric field caused by the bottom tape pointing up. And then, of course, in the bottom charge, that's light blue, that's the bottom piece of tape. I did draw the forces on that as well. However, we are mostly focused on the dark blue point charge. Of course, those two forces are evened out as that piece of tape is no longer moving whenever we took the measurement, and that is to suggest that the force of gravity is equal to the force from the electric field caused by the bottom piece of tape. This is another model, or diagram, I should say, of the experiment, and it kind of shows exactly what we're doing. So we're charging tape A and tape B the same way, so they should acquire the exact same charge. Then we have a 1 centimeter displacement on tape A, or of tape B, once we hold tape A close to tape B. So these two pieces of tape are charged the exact same way, therefore they should have the same charge, and so they should repel. We hold tape A close to tape B, and we see the displacement that tape B has from tape A, and that gives us the distance in the formula to determine the charge, Coulomb's law. That gives us the distance, and then of course we have the force of gravity that tells us what the force is. And so once we equate the force to Coulomb's law, trying to solve for that charge, we can solve for that charge. And our results got 4.9 times 10 to the negative ninth coulombs, or 4.9 nanocoulombs of charge on each tape. We do make two assumptions, though. We treat the long tape as though it is a point charge, and we do this because if all the charges along the tape are acting on all the other charges along the other piece of tape, then we can model them as just two single charges, or two single points accumulating the entire force. The same way we can model huge objects in their force of gravity just by the center of mass. And then we also assumed each U-tape had the same amount of charge evenly distributed along the length because of the way we ripped it off. We ripped it off evenly and with a smooth pattern across the table. Therefore, it's natural to assume that the piece of tape acquired similar charge along the entire piece of tape, and that allows us to model as a point charge. So here's my code. I have K, of course, the constant K, then G, constant G, little g. The mass of each tape was 0.00022 kilograms, and the distance that was displaced was 0.01 meters, and I scaled the electric arrow and the force arrow, and then of course I have the electric field the electric field function. And then in the next slide, I visualized, that's where I put all my visualization code to make that model before, where I define the vectors of the top and bottom position, starting at the origin to make it easier. I create point charges, I give them the charge that was calculated from before, and then I have the electric field on the top, electric field on the bottom, the force on the top, the force on the bottom, and then the gravitational force on both the top and bottom. And then I draw the arrows. I draw the arrows of the weight forces, electric forces, and electric fields on both dots. So a little bit of discussion. What the electrons had a positive charge and protons had a negative charge, nothing would change about the experiment. I mean, if you have a deficit, the charged piece of tapes had a deficit of electrons, therefore they got a positive charge. But if they if protons were negative instead of positive, then a deficit of electrons would just mean that it has a more negative charge, and two negative charges still repel each other, so nothing would really change. Why is it important to handle the charge states as little as possible? Because if you handle the charge states too much, you will then take away some of the charge by adding electrons to the pieces of tape. So it's important to touch it as little as possible to make sure the pieces of tape stay charged and nothing else and the experiment can work properly. Conclusion, we got 4.9 nanocoulombs after being stripped from the bottom piece of tape. There were many sources of error, including accidental touching of the tape and unsteady hands when putting it close.